the enthusiasm of students as well as faculty members to listen to our eminent professors, Professor Khattak, Professor Rajaram Nityananda, Professor Anurag Sharma, and Professor Vijay Singh. Before we start, I would like to express my gratitude towards National Academy of Science, India Delhi chapter, an academy with an objective of promoting science and research and always ready to extend its help by sponsoring workshops and seminars for the enrichment of researchers, teachers, and students. I would also express my sincere thanks to our principal, Dr. Anjula Bansal, for always be a pillar of strength in all our endeavors. This seminar is the collective effort of teachers of Department of Physics of our college. Dr. Pushpa Bindal, who is also the convener of this program along with me, worked tirelessly to materialize the event. All the other faculty members also extended their support and cooperation. I would like to inform that our principal, Dr. Bansal, is not keeping well, hence could not join the inaugural session. She has sent her blessings for the event. Now I invite Professor Ajoy Khattak for the inaugural address. We all have grown up reading books of Professor Khattak. It's our privilege to see him here and listen to his words of wisdom. Professor Khattak.
Thank you, Seema. Professor Anurag Sharma, Dr. Pushpa Bindal, Dr. Punita Verma, Dr. Seema Gupta, Dr. Rachana Kumar, Dr. Triranjita, everyone associated with the Kalindi College, all faculty members and students. It's my great pleasure to be participating in this important seminar on exploring physics for the benefit of students, not only of Kalindi College, but for all those who are participating in this workshop. Going beyond the classroom is a very important thing for any college, and knowing what all going on other than the curriculum is of great relevance and great importance for the students. And therefore, such workshops play a very important role in the growth of the academic community, particularly the students of colleges. So I'm extremely happy that Dr. Pushpa Bindal and Dr. Seema Gupta have taken this initiative in organizing the workshop. And in the past also, they have organized several workshops, and Kalindi College has been really very active in organizing such workshops, which I'm sure is of great benefit to student community at large. And with the technology that we have, namely this technology, not only it benefits the students of Kalindi College, but not only students in Delhi, but throughout India. In fact, there can be, in principle, participation from the entire world. That is the beauty of technology that we have with us. And it is for us, teachers and students, to use this technology wisely. I will say a few words about the National Academy of Sciences India. Maybe Professor Anurag Sharma will also speak on that. This is the oldest science academy, and it was started in 1930 at Allahabad, which is now known as Prayagraj. And, most students may not remember, we were not even independent at that time. So getting money, financial grants was extremely difficult. And with very little money to start with, Professor Saha and his colleagues started this academy to have interaction, to have a general awareness of the masses, of the advantage of science, of the role that science and technology plays in our day-to-day life. And it has become so important in today's world. So National Academy of Science, which we abbreviate as NASI, tries to play a very important role through its various chapters, which are scattered throughout the country. There are about 25 chapters, and they promote exhibitions, they promote workshops, they promote short courses and things like that. And even we in the past have supported projects, and Kalindi College has been recipient of several projects, and I'm very, very happy and proud of that. So with this introductory words, I'm really very happy and would like to congratulate Dr. Pushpa Bindal, Dr. Seema Gupta, and all her colleagues who have made great efforts in organizing this workshop and making it, and I hope it is successful. Thank you, Seema.
Thank you, sir.
Thank
Thank
you.
you so much.
Thank you so much, sir. We are honored that you accepted our invitation and gave us another chance to listen to you. Thank you so much, sir. Now I invite Professor Anurag Sharma, who is the Emeritus Professor and Chairman of NASI Delhi Chapter, for his inaugural address. Professor Anurag Sharma, please.
Yeah, good morning to everyone. I'm really very happy to be associated with this event. And I welcome Professor Khattak all the way from the US to this particular event. Of course, he has been part and parcel of NASI family for a long time. In fact, this chapter was steered by him in various capacities, and he has now handed it over to me, and I hope to do a job which is at least as good as what he has done in the past. This event is, of course, is an interesting event where we are exploring various concepts in physics. The four speakers will be doing that. NASI has been associated with such events for quite some time, and Delhi chapter has been supporting many webinars and workshops, some of which have been organized by the Kalindi College, by Pushpa and Punita and many others. And these kind of activities really are part and parcel of NASI. NASI, apart from being an academy, is also has a mandate to support and expand science to school children, school students, and college students in particular, which is a little different from other academies in that sense. And so the Delhi chapter also does the, sort of reflects this particular mandate, and we keep organizing these kind of activities. We also support some small student projects. In the past, they have been done, and we continue to do so, where the students are mainly involved, guided by college teachers or school teachers, and some modest amount of money can be given for supporting such activities. Interaction with school students, as I said earlier, is also one of the mandates, and we would like more and more college teachers to sort of engage in that particular activity. So these are the gamut of activities which NASI is mandated with, and Delhi chapter goes along with these particular activities. So this is also one of the activities like that. Last month we had a good workshop on virtual experiments, and this is which was also done by Kalindi College, and this is again being done by Kalindi College. So I would like to thank the Kalindi College administration and congratulate the organizers that they are able to do such good seminars and workshops. So thank you very much to all of you for having joined. I'm sure most of you will benefit from these activities. Thank you.
Thank you, sir.
Thank you, sir. Thank you so much. Thanks for your encouragement and support, sir. We are really thankful to NASI to believe in us and ready to be associated with our projects. Thank you, sir. So now we start with the first session of the national workshop. So first session for today is the Fiber Optics Revolution by Professor Ajoy Khattak. It's my privilege to introduce Professor Ajoy Khattak. Professor Ajoy Khattak is a renowned Indian physicist and author of many physics textbooks. He is currently Professor Meghna Saha Fellow of National Academy of Science, India. His research interests are in fiber optics and quantum mechanics. In recent years, he has taken a keen interest in bringing the genius of Albert Einstein to the wider public and was invited to present a TED Talk, Inside Einstein's Mind, in 2017. Professor Khattak has written over 170 research papers and more than 20 books. His undergraduate textbooks on optics and his monograph on inhomogeneous optical waveguides has been translated to Chinese and Persian. His other books include Quantum Mechanics, Theory and Applications, Fiber Optics, Optical Electronics and Lasers, and a popular book on Albert Einstein, The Story of a Genius. In 1995, he was elected Fellow of the Optical Society of America for distinguished service to optics education and for his contribution to the understanding of propagation characteristic of gradient index media, fibers, and integrated optical devices. Professor Khattak received his master's from Delhi University and PhD from Cornell University, USA. He joined the Indian Institute of Technology, Delhi in 1966 and retired as an emeritus professor of physics at IIT Delhi in 2007. He is the recipient of many prestigious awards, which include Shanti Swarup Bhatnagar Prize for Science and Technology, Physical Sciences, 1979, by the Council of Scientific and Industrial Research. Galileo Galilei Award, 1998, by the International Commission for Optics. Esther Hoffman Baller Medal, 2003, by the Optical Society of America, and SPIE Educator Award, 2008, in recognition of his outstanding, unparalleled global contribution to the field of fiber optics research and his tireless dedication to optics education worldwide. It's our honor that today we have Professor Khattak with us and we have another chance to listen to him. Professor Khattak. I stop sharing my screen.
Thank you. Thank you, Seema. Shall I share my screen?
Yes, sir. You can now share. I have stopped sharing my screen, sir.
Can you see my slides?
Yes, sir. Your slides are visible.
Okay. Thank you, Seema. Thank you, Pushpa, for inviting me to this important workshop. I'll be speaking on the fiber optics revolution, but before that, I will tell you a bit about optics because the title of your workshop is exploring different aspects of physics. So I thought that I will spend a little time on the importance of optics and photonics. So the photograph that we have on the first slide shows a red laser beam guided through an optical fiber, which was fabricated at the Central Glass Ceramic Research Institute in Kolkata. So I would like to spend a few minutes to tell the students, these are all very simple concepts, why study of light has become so important. UNESCO declared 2015 as the International Year of Light. Why 2015? Because 1000 years before that, in 1015, Alhazen, who was in Mesopotamia, now which is in Iraq, wrote the first book on optics, which was entitled Kitab al-Manazir, which was the first book on optics. This photograph shows the cover page of a translated edition of Alhazen's book on optics. In proclaiming 2015 as the International Year of Light, the United Nations recognized that applications of light science and technology are vital for existing and future advances in medicine, energy, information and communications, fiber optics, agriculture, mining, astronomy, architecture, archaeology, etc., etc. Then in 2018, UNESCO declared May 16th as the International Day of Light. Why May 16th? Because the first successful operation of the laser was done by the American physicist and engineer Theodore Maiman on 16th May 1960. As all of you know, he first produced the first laser, in fact, a first ruby laser, and in his hand is shown the ruby laser that he had first fabricated in 1960. And as we all know, the discovery of lasers has led to tremendous benefits of society in communications, healthcare, and many other fields. And one of the main advantage of the laser beam is its high directionality. If you have a light bulb, it radiates energy in all possible directions. But on the other hand, as in the photograph on the right shows, the laser beam is highly directed and therefore it can be focused to a narrow spot. So here is a 2 millimeter wide, 2 milliwatt laser beam being focused at a focal of a lens whose focal length is about 2.5 centimeters. So which is about the focal length of your eye. So if you use the red laser beam, then the area of the focused spot is about 7 into 10 to the power of minus 10 meters square. And if you have a 2 milliwatt laser, then the intensity will be 3 megawatt per square meters. Such high intensities will damage the retina. So never look into a seemingly innocent low power laser beam. So the point that I'm trying to make is, whereas it is safe to look at a 1000-watt electric bulb, but it is very unsafe to look at a 2 millimeter directed laser beam. And because focused laser beams produce extremely high intensities, it results in very important devices for the industry and also defense. Here is a laser beam drilling through concrete. And this particular photograph is from RRCAT in Indore, Raja Ramanna Center for Advanced Technology. And therefore, a fiber laser can be cutting through steel. And as you all know, laser beams are now extensively used for eye surgery and in numerous hospitals throughout the world. And powerful laser beams can create temperatures. Focused laser beams can create temperatures of the order of millions of degrees Kelvin, and which result in the production of fusion processes. And therefore, we can generate fusion power. Right now, the power that is input, that is required to create the laser beams is slightly more than the power that is created. But we are hoping in about a few years' time, it will be the other way around. That is, the fusion power that is created is more than the power that is required to have the large number of laser beams. And when that happens, you will have a fusion reactor. And that will solve the entire energy problem in our world. There is some line coming in this slide. I don't know how. Oh. Then, you know, the 2018 Nobel Prize in Physics was awarded for groundbreaking invention in the field of laser physics. So laser physics has become extremely important even as far as basic physics is concerned. And half of the prize money was given to 92-year-old Arthur Ashkin, who passed away only a few weeks back, for his contribution to optical tweezers and their applications to biological systems. So this is a tweezer holding a diamond, small diamond piece. This is actually, so you want to trap a virus or a large molecule, thing which is about a millimeter in bead, in a millimeter in diameter. And so that is the concept of the optical tweezer. And that is based on the principle that light that is emitted, which was put forward by Einstein in 1905, radiation is emitted in discrete amounts called quanta, which has energy h nu, and which was a revolutionary concept and eventually led to the development of quantum theory. And these light quanta later came to be known as photons, whose momenta was given by h nu by c, where h is the Planck's constant, c is the speed of light in free space, which is about 300 million meters per second, and nu is the frequency. Because now, if you throw a cricket ball or a tennis ball on a stationary train, which is on a frictionless track, then because the ball changes its momentum, direction of the momentum, it imparts from the law of conservation of momentum a slight momentum to the train itself, and the train will start moving if the rails are completely frictionless. And so therefore, when light falls on a mirror, the photons are coming in from this direction, they change their direction, the momentum changes. So therefore, a very tiny amount of momentum is imparted to the mirror in the forward direction. So if you have a light beam, if you have a laser beam falling on a lens, then because of the momentum, because after refraction, the momentum of the direction of the momentum of the photon will change. And so therefore, it will impart a small momentum to the lens itself. So here is a laser beam. This is the transverse section of a laser beam. The intensity that you see, for example, in a helium neon laser beam, the intensity is maximum on the axis, and it fades away almost like a Gaussian beam. So these two rays are all equally intense, and it falls on a bead which is, let us suppose, a micrometer in diameter, micron size. So the ray which comes here gets refracted like this, and the ray which comes here gets refracted like this. So the ray which undergoes refraction in this direction imparts a momentum in this direction, and this ray imparts a momentum in this direction, force in this direction. So the net force is very small in the forward direction. And so therefore the bead does not move. However, when the bead is displaced from the beam center, this portion of the beam is more intense than this because it is closer to the center. So therefore F2 is larger in magnitude than F1. And so therefore the bead will be shifted. There will be a force exerted on the bead which will tend to move it in the direction of the axis. So the rays, therefore the laser beam causes a net force to be applied back toward the center of the laser. Thus the bead is held near the center of the laser beam. And in fact, if you have a focused laser beam, then what will happen? If it is displaced from the axial, a focused laser beam is made to fall on the sphere, which is of micron size, which in addition to keeping the bead at the center of the laser, also keeps the bead in a fixed axial position. So it gets trapped here. So using a focused laser beam, you can trap a micron sized particle. That is the principle of the optical tweezer. And if you go to YouTube, I tried to show you the video, but unfortunately I am unable to show you right now, but it is very easy. If you go to YouTube and write optical tweezer systems, then you will get a large number of experiments in which they will show that micron-sized beads can be moved around with the help of laser beam. So that is the beauty of optical tweezer, for which half of the Nobel Prize was given to Arthur Ashkin, and it is now an extremely important device. Then remaining half of the Nobel Prize was given to Gerard Moreau and Donna Strickland for chirped pulse amplification. This is Gerard Moreau receiving the Nobel Prize, and this is Donna Strickland from University of Waterloo in Canada receiving the Nobel Prize. They did this work at University of Rochester when Donna Strickland was a PhD student under Gerard Moreau. So this is based on the principle that if you have a pulsed beam, if you have a pulse, let us suppose you switch on a laser and switch it off, you produce a pulse, and you pass through a device where the group velocity decreases with the wavelength, then the pulse will broaden. This is the phenomenon of dispersion, and it will get chirped. Because as it broadens, if you take the Fourier transform of this pulse and the Fourier, they are the same. It will be the same because it's a linear system. But the peak power will come down, and the peak power can substantially come down, which can then be amplified, and the peak power made larger. If you use this pulse, then it can damage the amplifier, so that for the amplifier not to get damaged, you first broaden the pulse and with reduced peak power, and then you amplify it. Then the amplified beam is then passed through a group velocity increasing with wavelength. It's a very beautiful physics. I have tried to explain this in my book on optics. So the pulse will get compressed with increase in peak power. So to quote Strickland, Donna Strickland, she has written, the technique involves, the CPA involves taking a short, low energy laser pulse, stretching it in the time domain to make a long, low energy pulse, and then low energy pulse is amplified. And you require a low energy pulse so that the amplifier does not get damaged, to get a long, high energy pulse before finally it compresses to form an unchopped pulse to get a short, high energy pulse. This is the basic principle of chopped pulse amplification, which is really quite simple. And such ultra short, high intensity laser pulses produced by CPA, the basic physics I just described, find extremely important applications in industry. For example, in cancer treatment, in many commercial products, in eye surgery, etc. Indeed, since 2011, CPA has been used in 24 million eye operations. Then, the 1997 Nobel Prize in Physics was awarded to Stephen Chu, Kohan Tanuji, and William Phillips for development of methods to cool and trap atoms with laser light. These are the three gentlemen. And when the 1997 Nobel Prize was announced, it was essentially using the optical tweezer of Arthur Ashkin. So Arthur Ashkin was very upset. That's what the story goes, that people used their method to get the Nobel Prize, but the method itself did not get the Nobel Prize. But eventually the Nobel Committee woke up and gave the prize to Arthur Ashkin also before he passed away. That was a great thing that the Nobel Committee did. Not all prizes are given. One of the greatest errors of the Nobel Committee is not giving the Peace Prize to Mahatma Gandhi, who was nominated 6 times before his death. And that is supposed to be. So Nobel Committee also makes some mistakes, but it in general awards prizes to some of the greatest physicists and persons. And then, as you all know, Dennis Gavor got the Nobel Prize for his invention of holography, and Glauber for his contributions in quantum optics, and Hall and Hansch for their contributions to the laser-based precision spectroscopy. So you see, so many Nobel Prizes are awarded in the area of optics and photonics. And then the 2014 Nobel Prize was awarded to these 3 gentlemen for the invention of efficient blue light-emitting diodes, energy-saving white light sources. And then very recently in 2017, you see, 2018 Nobel Prize was in optics, 2017 Nobel Prize was awarded to these 3 gentlemen for contributions to the LIGO detector, laser interferometry gravitational observatory detector, and observation of gravitational wave. But if you look at the experiment, it is all optics. It is all the LIGO, as I just now said, stands for Laser Interferometer Gravitational Wave Observatory. It's a gigantic interferometer. And 1.3 billion light years back, there was a violent collision between 2 black holes. It generated very powerful gravitational waves, and which were detected here. The gravitational waves, each arm of the interferometer is about 4 kilometers long. And each arm of the interferometer was affected slightly differently, so that the interference pattern got shifted. So it is all optics. And the good news is there is a LIGO facility that is going to be built. There are right now 2 LIGO facilities. The 3rd one is getting built in Japan, and the 4th one is planned to be built in India. And when it comes to India, I hope I'm still there to see it. I would like to see that. So there will be a large number of people trained in optics, trained in optical precision experiments, and to design the interferometer and play around with it and work in the forefront of physics. So therefore, what I have tried to tell you in the previous slides, I hope I have been able to tell you that why study of light or of photonics has become extremely important, not only for students of physics, but more so in engineering. And I keep repeating this in all institutions, because unfortunately in our undergraduate curriculum, there are courses on optics and photonics, but not as much as there should be. And in engineering, it should be compulsory. In most Western universities, there is photonics, which is compulsory for all electrical engineering students. And in India, it is not that way, but it should be. Photonics should be a compulsory thing to study, at least an optional paper to study. So I'm going to speak the rest of my talk on fiber optics, which has been my own, and even Professor Anurag Sharma has made very important contribution to fiber optics, a technology that has created a revolution and has made phone calls free. And this video conferencing today, I'm speaking right now from the United States, and there's the almost free video conferencing that is possible because of the fiber optic technology, which has pervaded the entire world, the entire communication system. And today you can talk to your friend. Only 20 years back, I would make a phone call to Bombay and it will cost me about 100 rupees for 3 minutes or something like that. Today, everything is free. You can talk to your friend in Australia or London or New York almost free of cost. You can see him or her. So that has been possible because of optics. So as you all know, around 1864, Maxwell predicted the existence of electromagnetic waves and said that light itself is an electromagnetic wave. And all wavelengths from gamma rays to radio waves travel in free space with an identical velocity of 299792458 meters per second. The difference between gamma rays and ultraviolet rays and microwaves and radio waves are the fact that they have different frequencies. So this is the visible region of the spectrum. The wavelength goes from 0.4 micron to 0.7 micron. The corresponding frequency in the green region is around 600 terahertz to 500 terahertz in the yellow region. As you all know, 500 terahertz means 5 into 10 to the power of 14 hertz. And the radio station that you have on in your car or your FM broadcast is 98.3 megahertz, which is 98.3 into 10 to the power of 6 hertz. So I'll first tell you briefly the light guidance through the optical fiber, which I'm sure all of you know. Total internal reflection, whenever there is a light hitting a rarer medium at an angle greater than the critical angle, then you have total internal reflection taking place. Although the phenomenon of total internal reflection has been known for 300 to 400 years, it was only in 1841 that Daniel Collardon, a professor at the University of Geneva, used total internal reflection to guide the light beam. So here is the water spout coming out from a jar, and the light gets trapped. And the light gets trapped because it undergoes total internal light guidance through total internal reflection. So you have in a optical fiber, you have a core, you have a cladding. Cladding is usually pure silica, having a refractive index of the order of 1.46. The core is silica, but with little bit of germanium, so that its refractive index is slightly higher, 1.47, and the total internal reflection takes place at the interface of core and cladding. So if you have a bare fiber, then also you have a light guidance. But if the light can quickly leak away from an unclad fiber, and hence the necessity of a cladding. Because if I have an unclad fiber and if there is another material touching it, then light will leak through. So cladding will not allow light to leak through. And the concept of cladding was put forward by Van Heel in Holland and to Hopkins and Kapani in the United Kingdom. I could not get the photographs of Van Heel and Hopkins, but there is Narendra Kapani, who passed away only a few weeks back at the age of 96. He wrote the first book on fiber optics. So these are the dimensions of the optical fiber that are now used in communications and even in sensors. The core of the fiber has if you single mode fiber, it has a diameter of the order of 10 microns. Even a multi-mode fiber, it has a diameter of about 50 to 60 micron, and the cladding diameter is almost always 125 microns, and then there is a protective jacket. And there is a light getting guided through the optical fiber. And the light that comes out is because of what is known as Rayleigh scattering. So what is scattering? if you have a alpha particle approaching a positively charged nucleus, then the alpha particle gets scattered. It gets repelled by the force and it's scattered in a different angle. This process is known as scattering and is a very important concept in physics. So here is a glass containing distilled water, and here you have put a few drops of milk. You can do this experiment at your home, and you have a laser beam. You see no light coming through. There is no scattering, almost no scattering. But because of the milk particles here, they are colloidal particles. They undergo not Rayleigh scattering. This is actually Meese scattering, and because of which you can see the light beam. And this, the very fact that you can see the light beam is a consequence, is a manifestation of the phenomenon of scattering. So the Rayleigh scattering is inversely proportional to the fourth power of lambda. So therefore, higher the wavelength, smaller will be the Rayleigh scattering. And since the red region has a higher wavelength than the blue region, so therefore the sky is blue. The sky is blue. The clouds are white. Actually, the clouds are white. That is not because of Rayleigh scattering. That is because of what is known as Meese scattering, because the water droplets are very big in size, and that scattering is independent of the wavelength. Molecular and atomic scattering it depends on Rayleigh wavelength, very sensitive. It is inversely proportional to the fourth power of the wavelength, and therefore the sky is red when you have a setting sun or rising sun, because the blue component is scattered out, which has a smaller wavelength, so it is predominantly scattered out, and so therefore the setting sun or the rising sun is red in color. But if you are in the surface of the moon, the sky is black because there is no atmosphere there. And the rising sun or the setting sun is completely white in color. So there are three areas in which the optical fiber is playing an extremely important role. One is the image transfer, second is optical communications, and the third is devices, fiber amplifiers, fiber lasers, fiber bright gratings, and so on. So in 1930, Heinrich Lamm, a medical student in Munich, first assembled a bundle of transparent fibers to transmit an image. So this is known as a coherent bundle. This is the front end of the fiber. This is the back end of the fiber. If this is bright, then this will be bright. If this is dark, then this will. So I've shown the image of the letter T being transported from one end to the other. And so here is a bundle of, say, thousands of fibers. And this can be about a centimeter in diameter or even less than that. So here is a human hand holding an optical fiber bundle, which is thin enough to be inserted. It can be inserted down the throat or through the anus inside the human body. And one can see in this example a stomach ulcer. So it has revolutionized medicine. And on the tip of the fiber, if you put a lens and you use a powerful laser beam, then you can almost destroy tissues and tumors and things like that. So it's a revolution that has happened, and it's a technology that one should be manufacturing such devices in India. Unfortunately, they are all imported, and they are also extensively used in almost all hospitals in India and through the country. So I don't know where this is coming from. So solar fiber optic lighting. Someone is playing around with it.
Sir, just a minute. Students, please stop creating mischief. If we catch you, you will immediately be asked to leave the seminar, and you will be punished for that. He is a very, very senior professor. He is our teacher. Please stop doing that. Understand and appreciate how much effort he is making for you. Please don't do it. Don't disturb others. I am interested in learning. If you are not, leave.
Just one second.
Actually, sir, sometimes it is not intentional. If you are joining from a phone, sometimes when you are joining from a phone, and if you swipe through the
हमारे पास
screens,
टाइम कितना है यार? 30 मिनट और है?
हाँ जी सर, 30 मिनट है.
25 I will try to finish.
So, sir,
Tell
the
me when I
message
have
to
to finish, so that I do not want to intrude. So another area in which recently the fiber optics is very playing a role is not glass fibers, not silica-based fibers, but plastic fibers, which have a diameter of core diameter 8 millimeter, cladding diameter 11 millimeter. Now they are used for transporting light from the roof. This is no solar energy. This is just transporting light from the roof to the inside of the room. And I personally feel that this has a tremendous potential in India. So you collect the sunlight through, these are the collectors, and you illuminate. And India is a country which is flooded with sunlight. And this is used, this is now being used in Western Europe, which has very little sunlight. And they are marketing this. This is an actual photograph of a room which is completely illuminated by optical fibers. Of course, if it's a rainy day, then of course you will not get light. But it's not a very difficult technology. But for example, the classrooms and offices in small villages where there is no electricity, optical fibers can be used to transport the sunlight to inside the room and create light there. So it is now a reasonably big industry in the Western Europe, and there is no reason why it should not be in a very big way. I'm trying to promote myself in states like Rajasthan, UP, MP, Gujarat, Maharashtra, where there is Punjab, where there is a lot of sunlight. So this is the actual drawing. This is the patent which allows you to collect the sunlight and transport it to different rooms. Unfortunately, the loss is very high. The plastic has a very high loss, and so therefore there is a lot of absorption that is happening. And plastic fibers can also be used to transport light from the bulb, can be 10 meters below, and it can be, signs can be used at the top of the bridge and things like that. We next consider optical fibers in communications. Higher the frequency of the carrier waves, higher would be the information carrying capacity. So gamma rays have a very high frequency, radio waves have much smaller frequency than that. So light frequencies are in the region of 10 to the power of 100 terahertz. Radio wave frequencies have megahertz, microwave frequencies have gigahertz. So therefore, light wave frequencies are about a million times more than the microwave frequencies, and are therefore capable of carrying much larger amount of information. So for example, a telephone line, the bit requirement is 64,000 bits per second. A standard television is 100 megabits per second, and high density television is about 1 gigabit per second. So in a typical fiber optic communication system, we have what is known as a digital transmission. An analog electric signal is transformed into digital system, and then it is passed through from one place to the other through the optical fiber. And when it is received, a part of it is lost, it gets attenuated and also disperses. There is also a dispersion, broadening in time. What is dispersion? As I mentioned earlier, there's a slight broadening in time. So pulses start overlapping. So in a good fiber optic system, the attenuation should be small, or we should have amplifiers, and the pulse dispersion should be small. And if I'm able to detect the individual pulses independently, then we can retrieve the original signal. So that is the basic layout of a typical fiber optic communication system. I thought I should tell you that the first optical communication system was built by Alexander Graham Bell in 1880. He called the photophone. In this system, and this photograph I have taken from the original paper of Alexander Graham Bell. In this system, sunlight was modulated by a diaphragm. Here is the diaphragm, and transmitted through a distance of about 200 meters in air to a receiver. This is the receiver containing a selenium cell, connected to the earphone. So this was the first experiment on optical communication. And Alexander Graham Bell later wrote that the photophone was the greatest invention I have ever made, greater than the telephone. Then between 1880 and 1960, there was not much work in communication using light beams because you require to modulate the light beam. And then as I told you earlier, a revolution occurred. The laser was fabricated, and suddenly laser light communication using the laser beam was taken up. Initially, people started communicating through the open atmosphere because of the directionality of the laser beam, but it was soon found that if there are dust particles or rain or cloud, then it will get severely attenuated. So in 1966, a very profound prediction was made by Charles Cow and George Hockham of Standard Telecom Laboratory in UK. And they said that because glass fibers were known at that time, Narendra Kapani had worked on that. Glass fibers and I must say Harold Hopkins, they had used the glass fibers for image transmissions, not for communication. There have been recent reports that Narendra Kapani should have got the Nobel Prize for optical communication. No, that is not correct, because he made those glass fibers primarily for image transmission. He didn't think of using it in communication, which has really been a great revolution. So glass fibers, Charles Cow said, and George Hockham, represent a possible practical optical waveguide with important potential as a new form of communication medium, provided the tiny impurities in glass are removed. Because of the tiny impurities present in the glass, they have a very large loss, about 1000 dB per kilometer, and even much more than that. Even the most transparent glass that you use in your windows has a loss of about 6000 to 10,000 dB per kilometer. But he said those tiny impurities in the glass have to be removed, and the attenuation should be brought below 20 dB per kilometer. So most of you would know, but even then I will tell you what is the dB. Loss of power in decibels is log of the input power to the base 10 divided by the output power. So if the output power and input power are the same, then it's a 0 dB, log 1 is 0, so it's 0 dB power loss. If output power is half of input power, then it is log 2, that's 0.3, that is 3 dB power loss. So 3 dB power loss is 50% power loss. And on the other hand, the power loss by a factor of 10, log 10 is 1, so alpha is 10 dB power loss by it's a logarithmic scale. Power loss by a factor of 100 is 20 dB, and power loss by a factor of 1000 is 30 dB. If you have an amplifier which has an 30 dB amplifier, then it is a power amplification by a factor of 1000. So the prediction was made by Charles Cow, as I had mentioned a few minutes back, in 1966. And throughout the world, after Charles Cow's prediction, throughout the world, people started purifying glass. And in 1970, Donald Keck and Robert Murrer and Peter Schultz at Corning Glass Works in the US produced silica fibers having loss of about, and this was a great milestone. In fact, few weeks back, 2 months back, I think, Peter Schultz gave a lecture and gave a webinar sitting in USA in India, and I heard him. He very beautifully, I think it should be on YouTube, he described the evolution of the processes that led to the great achievement of these three people in 1970. Many people feel that, as I will tell you in a minute, that Charles Cow received half of the Nobel Prize. Many people feel that these three gentlemen should have also received the Nobel Prize. So the loss is this is a typical loss curve by late 80s, early 80s, late 70s. The lowest loss occurred of the fiber. This is loss in dB per kilometer, and the horizontal axis is the wavelength. And the lowest loss is 1.5 at 1.55 micron, which is in the infrared region. And the lowest loss is about 0.2 dB per kilometer. And these peaks are due to tiny amounts of impurities that are very, very difficult to remove. These are known as water peaks. And these are due to the presence of iron or cobalt or chromium present in the glass. But the envelope of the curve is 1 over lambda 4, which is the Rayleigh scattering, which I had described earlier. So please see, there is a dip here, 1.3 micrometer. The first generation and the second generation optical communication systems operated at 1.3 micron or 1300 nanometer. And now almost all communication systems operate at 1.55 micron, primarily for two reasons. One is that it is the lowest loss and the availability of optical amplifiers at this wavelength. There is a company by the name of Sterlite. Many of you would know that they are manufacturing communication grade optical fibers globally. So we have a company in Aurangabad which makes those fibers. So here is Charles Cow, received half of the Nobel Prize, 2009 Nobel Prize in Physics, although many people feel that there are many others who also deserve the Nobel Prize. So the chair of the Nobel Committee said, Charles Cow's discovery made in 1966 led to a breakthrough in fiber optics and revolutionized the way in which information can be transmitted globally. So why glass fibers? Glass is a remarkable material which has been used for thousands of years, and glass does not solidify at a discrete freezing temperature. But when you heat glass, it will become viscous. It will be neither a solid nor a liquid. And when it becomes viscous, you can draw it in the form of a fiber. So that is the beauty of glass. So glass does not solidify at a discrete freezing temperature, but gradually becomes stiffer and stiffer and eventually becomes hard. In the transition region, it can be easily drawn into a thin fiber. So this is the transition region. This is you become so hot that it becomes soft and you can draw it in the form of a thin fiber. There was another breakthrough in 1970. These room temperature semiconductor lasers were discovered by Alfarov and Hayash and Panish. So I will spend the rest of my time on one of the devices, and that is the optical amplifier. How do you amplify? Because there is a small loss, even if you have a 0.2 dB per kilometer loss. So for 80 kilometers, if the light is propagating through a distance of 80 kilometers, then 0.25 dB per kilometer loss multiplied by 80 is 20 dB loss. So a milliwatt power will become 10 microwatts. So the power becomes so small that the receiver will not be able to detect it. So for long distance transmission between Delhi and Bombay or New York, there should be enough optical power at the receiver end for error-free detection. So therefore, to travel long distances, we need to amplify, and we require optical amplifiers. Can fiber loss be compensated optically? We can have direct amplification of optical pulses by using headphones. Erbium doped fiber amplifier. Now listen, I'm talking to the students. Listen to this carefully, because if you understand this, then you will be able to understand the working of the laser. So in 1917, Einstein published an extremely important paper entitled On the Quantum Theory of Radiation, in which he was able to predict stimulated emission. I'm sure most of you know this, which eventually led to the development of the laser. So if there is an atom sitting on a higher state, it makes a transition. Light is emitted, light quantum is emitted, and this is known as spontaneous emission. And if you have a light wave of the appropriate frequency, the frequency should be such that h nu is very close to E2 minus E1, then it can, the atom in the in the lower state absorbs this radiation and gets excited to E2. This is known as stimulated absorption. Now these two were known. Spontaneous emission was known, stimulated absorption was known. What was not known, the existence of stimulated emission. And that Einstein said that radiation of this frequency can also stimulate an atom in a ground state, and this can absorb the radiation, and you will have a stimulated emission. What he did not say, and what Richard Tolman said in 1932, 15 years later, that a light wave through the process of stimulated emission will get amplified. So this is what the acronym LASER stands for. Light amplification through stimulated emission of radiation. Light amplification through stimulated emission of radiation. So what Richard Tolman in later in 1924, not 32. This is a photograph taken in 32, but Tolman's paper was in 1924, where he said that a radiation of the appropriate frequency, when it sees an atom in an excited state, stimulated emission will occur, which will result in an amplification of the beam. And what Einstein had said, that the probability of the stimulated emission is the same as probability of stimulated absorption. And so therefore, in a normal temperature, in thermodynamic equilibrium, there will be larger number of atoms in the ground state, smaller number of atoms in the excited state. So therefore, the probability, there is a radiation of this frequency coming in. So there will be larger number of stimulated absorption, smaller number of stimulated emission, because the number of atoms are small, resulting in the attenuation of the beam. I hope it is clear. On the other hand, and this is what Charles Towns said, you see, many people have asked the question that stimulated emission was discovered in 1917, and it took such a long time for the laser to be discovered, because people did not think that population inversion can occur, because that violates thermodynamic equilibrium. So Charles Towns said that if somehow I can have a larger number of atoms in the higher state, then you have created a state of population inversion. Then the number of stimulated emissions are larger than the stimulated emission, stimulated absorptions, resulting in an amplification of the beam. So this is again light amplification through stimulated emission of radiation. So this is how I used to, when I used to teach lasers to my undergraduate students, first year or second year students at IIT. I will first teach them erbium doped fiber amplifier, and I will tell them the concept of optical amplification. So listen to this carefully. You have a fiber. So in the core of the fiber, you have a small amount of erbium, about 40 to 400 parts per million. So the erbium atoms in a glass silk matrix, the erbium atoms form bands, large number of levels which are very closely spaced. So it's like a band, like in a semiconductor. So the difference of energy is 1.3 electron volts. And that corresponds to a radiation of about 980 nanometers. So it need not be 980 nanometer, 990, 970. That also can, because these are very broad bands. It need not be very exact. So a 980 nanometer laser beam will excite the erbium ions from the level E1 to E3. Now the E3 level has a very short lifetime, 1 microsecond. And it makes a transition to the level E2, which is also a broad level, but which has a long life, 10 milliseconds. 10 milliseconds is also a very small time, but it is 10,000 times more than this. So if you have a powerful laser beam, powerful 980 nanometer laser beam, it will go up and immediately come down here and just sit there, because it has a very long life. And when it makes a transition, say spontaneous emission, you have a 15-20. But if the power level is very high, then atoms will keep sitting on E2 because this is it's almost stable. And so you can create a state of population inversion, that the number of erbium ions in E2 will be much larger than the number of E1. So when this happens, there will be larger number of atoms in the level E2 than in E1. And then a 1.55 micron, this is 1.55 micron, beam can get amplified. So that is the basic principle of an optical amplifier. So light from the pump, this is the pump, and it supplies energy to elevate the erbium ions to excited state. Propagating optical signals induce stimulated emission. So you have a signal in excited ions and therefore amplified. So this is basically a very simple construction. Of course, the actual fabrication is slightly difficult. But you have a coupler, you have a pump laser at 980 nanometer. It injects the 980 beam, and this is about 20-meter long erbium doped fiber. This part of the fiber is doped with erbium. So this is the active region. So this 980 nanometer makes it inverted. So the incoming signal sees an inverted medium, that is larger number of atoms in the E2 state and the smaller number of atoms in the E1 state. This pump creates a state of population inversion. When this signal sees a state of population inversion, it gets amplified. So that is the beauty of the erbium doped fiber amplifier. This is the simplest optical amplifier that I can think of. Once you have this optical amplifier, you put between the two mirrors and you have a resonator and a laser. So that's how I used to teach laser to my second year students at IIT when I used to work there. So a pump excites from E1 to E3, and that is a 980 nanometer pump in the infrared region slightly. And then it creates a population in a very larger number of atoms. So a signal at 1550 gets amplified. So these are the erbium doped optical fiber which are developed at CGCRI. They have a very beautiful facility. And this is not very simple to prepare communication grade optical amplifiers. They supplied the erbium doped fiber to a company in Cochin, Nest, and they fabricated EDFA. I don't know whether they have been, and this is the fiber EDFA in production at Nest, Cochin. So there is some industry going on, but not as much as one there should be, because it's all the cost. The production capability of Indian companies are much smaller than in China. And so therefore they can sell it cheap. And even if we go to market and buy, we will of course buy a cheaper product. And so therefore they cannot compete with what is produced in China. That is the whole trouble. This is a compact EDFA. I always show this because it was done by New Photon Technologies, the president of which is Dr. Ramdas Pillai, who is one of our former students. He's now settled in the USA, but he has also created a company at Trivandrum. So this is the size of an EDFA. And this is a 25-cent coin, which is of same size as a 2 rupee coin or a 1 rupee coin. So this is a typical gain flattened EDFA. Vertical axis is the gain and the horizontal axis is the wavelength. So you see, you have a 30 dB flat gain. It is possible. This is a typical commercially available. So all wavelengths can be simultaneously amplified. And this is not possible in a conventional amplifier. And so EDFA created a revolution when it was discovered when it was fabricated for the first time in around in 1989 and 90. So this is a conventional repeater. So in this, I don't have the time to go through. Each wavelength has to be amplified separately. Here, all wavelengths can be simultaneously amplified. So what one does is, you have a large number of wavelengths which are multiplexed into a thin fiber and amplified simultaneously, all wavelengths. They are shown in different colors, but they are not really different colors. They are all in the 1.55 micron, 1.53, 1.54, 1.545, and so on. Hundreds of wavelengths. Each wavelength carrying a lot of information. So it's known as a wavelength division multiplexed system. You have a large number of wavelengths passing simultaneously through a hair-thin fiber, getting amplified by the Headphone. And then there is something to compensate for the dispersion also, which I have not done. Everything cannot be done in 1 hour and gets transported. And the distance between two amplifiers is about 80 kilometers, 80 to 100 kilometers. So you see, the number of channels, that is number of wavelengths passing through a hair-thin fiber. There was only one wavelength can pass through, and they can be periodically amplified. Suddenly, when in the 90s, the Headphone came into the market, by 2001, 200 wavelengths, and now probably, I do not know the latest figure, about 500 or 1,000 wavelengths simultaneously through one hair-thin optical fiber. And because of this, the price came down, and in 2001, Alcatel, I should provide a more recent slide. Alcatel propagated simultaneously 256 wavelength channels through one optical fiber, sending 10.2 terabit per second of information. That is equivalent to 150 million telephone channels through one hair-thin optical fiber. It is because of this reason that today you can speak to your friend in New York almost free of cost. That is the revolution. You can see his photograph. You can do a WhatsApp call. How can you do that? It is through fiber optics and Headphone. Those and the low loss optical fibers and the Headphone. And so fiber connects across oceans and undersea, and it's a revolution that has occurred. And this is a typical fiber optic cable, which contains every 80 kilometers the amplifier embedded into this cable, submarine cable. Even in India, most of the big cities are connected. Even with I live in Housekhas, and at the curb you have this thing, and there are many areas in Gurgaon where they say that they have fiber to the home. And that will be a great revolution where a single fiber to the home can, your internet, your TV, your telephone, everything will be connected to that. So erbium doped fiber amplifiers are extensively used in fiber-based optical communication systems. Headphone was invented in 1987 by David Payne and his collaborators at the University of Southampton, and Emmanuel de Silver and his collaborators at AT&T Bell Lab. The Headphone brought about a revolution in fiber optic communication systems. Many people feel that they should have also had a share of the Nobel Prize. And it is the fiber optics and development of Headphones which have made phone calls and video conferencing almost free. So I will conclude by saying, I will tell you one more thing, that the basic components of a laser are active medium and an optical resonator, which resonator provides a frequency selection and optical feedback. So if you put the active medium, like the erbium doped fiber, between two mirrors, and introduce a pump, you will have a laser. And the resonator makes the beam pass through and oscillate, and only certain frequencies get amplified. Those are the resonator frequencies, and this is all this is the laser. And so therefore, so you all right, let me not go through that. That's a very, you see, this is the fluorescence spectrum. This is the fluorescence spectrum. You slowly increase the 980 nanometer pump, and suddenly it starts lasing. It's one of the most beautiful experiments in physics. And an amplifier becomes a resonator and the polished surfaces of the ends, and I have seen this myself, and in our lab, the amplifier transforms itself into a laser. So this is what a laser consists of. You have a rare earth doped, like a erbium doped fiber, or rare earth doped fiber, neodymium, erbium, and so on, and you have mirrors at the end, and this is a fiber laser configuration. In 1961, 1 year after the discovery of the laser, Elie Snitzer took a glass fiber whose core contained neodymium ions, wrapped the fiber around a flash lamp, and when suitable optical feedback was applied, a laser was produced. That's only 1 year after the demonstration of the first ever laser, the first fiber laser. And this is another revolution that has happened. When many people feel Elie Snitzer. No, one of the greatest errors of Nobel Committee is not giving the Nobel Prize to Theodor Neumann. He has created a revolution. Theodor Neumann and Elie Snitzer, they all are in that category. And we have also facilities at RRCAT, Raja Ramanna Center. They have a big program on continuous wave fiber laser, 40 watts and many more. And you can do welding and hole drilling. Pushpa, can I have 5 more minutes? Or I should stop here? Are you there? Or?
No, sir. Sir, actually, Professor Rajaram has joined me here. If you want, you can continue for some more time. I'm trying to contact him.
All right. So you see, I will let me go through this. This is the Newton's rings experiment.
Hello.
So you are, all of you have done this. Light reflected from this surface and light reflected from this surface produce an interference, and you see these beautiful Newton's rings. So if you have layers like this, then you can do something like this, that the thickness is such that each reflection is in phase. That will occur for one wavelength. And that wavelength is the Bragg wavelength. So this is N0 plus delta n, and this is N0 minus delta n. And the Bragg wavelength will correspond to 2 N0 lambda. Lambda is capital lambda is the periodicity. So if you have layers of refractive indices, then they will all add up in phase for a particular wavelength. And so therefore, look at this is known as the basic principle of the fiber Bragg grating. And it's a very beautiful device. You have a polychromatic light beam, white light beam, falls on a fiber Bragg grating, fiber in which you have periodic variation of refractive index. Pushpa, whenever you want me to stop, please tell me.
Sir,
Whenever
please
you
continue.
get hold of,
Sir, please continue. Please continue.
Have you been able to contact your next speaker?
Yes, sir. He's joining.
Yeah, sir. I will take that 2 minutes. So then this is the reflected spectrum. I don't have the time to go into the theory. So this bandwidth can be as small as 1 nanometer or even 0.1 nanometer. So you see, there is a photosensitivity with which you can write this grating. I will not go. So you see, you have a fiber in which you have a grating of one periodicity here, another periodicity here, another periodicity here. This reflects lambda 1, this reflects lambda 2, this reflects lambda 3. And let us suppose lambda 2 gets stretched. If it gets stretched, then the wavelength will shift. And you can find out the stretching. And so therefore, one of the very important applications of the fiber optics has been in the sensor technology. So all civil structures, bridges, and tall buildings are now embedded with fiber Bragg gratings. And this Mississippi River bridge collapsed, and people say this is the collapse of the bridge. People say that if this was embedded, if could have avoided this ship by real monitoring of the health of the structure. So CGCRI Kolkata have measured the temperature of this high tension cable by using fiber Bragg gratings. So this is one area, another very, very important area related to fiber optics, which has also created revolution. of having very sophisticated sensors in very remote areas, and you can play around with that from a glass distance. Of course, this is another topic on which one can spend hours. So I will, and then one more thing. So you see, you don't require a mirror. You write a fiber Bragg rating, and that will act as a mirror. It's a beautiful thing that you have an Earth fiber, and at the end you write 2 fiber Bragg ratings. So that will act as a mirror, and you have a seed laser, and which you can amplify with another Earth fiber. So I will skip all this, and many other experiments can be done. The references are, we wrote this book with Professor Tyagarajan, and this is my latest edition of my optics book. I have several chapters. This is a little advanced level book. This is a little lower level book for undergraduate students. Then we have a large number of books from our group. This is by Professor Anurag Sharma, Professor Vishnu Pal, Professor Shamal Bhadra. And this is again by Anurag Sharma. We developed a software. Then there is another software and experiments and so on. Thank you. Thank you, Pushpa. Thank you, Seema. Thank you, everyone.
Sir, thank you so much. it was such a nice talk, an excellent talk as usual. You are just a master. You are too good for this. Sir, yeah. Sir, I would like to tell the audience that Professor Khattak probably was the first scientist, first academician who started research in the field of fiber optics. So he is definitely a pioneer.
No.
Yes,
Actually,
sir. Yes, sir.
No, there is a correction there. Professor Sodha asked me. So Professor Sodha
yes, I know that, sir. Professor Sodha asked you, but you started the research. And the first batch of students have done their PhD with him in this area. They themselves are now so renowned, highly established academicians, like Professor Tyagarajan, Professor Anurag Sharma, Professor Paul, Professor Arun Kumar, Professor Inakshi Sharma. All of
you
them,
are absolutely right, Dr. Pushpa Bindal. My students are much better than me.
No, please, sir. We can't even, we always look up to you. You are inspiration personified. Absolutely. I can vouch for that. I can vouch for that.
Yes,
so
sir.
actually, nobody could have been better than him to, give this talk on fiber optics. So thank you, sir. It was really good. Very, very good. And now I think there are just 1 or 2 questions in the chat box. So may I take them?
There is a question on Cohen Tanuji paper on optical tweezers. You see, Cohen Tanuji used optical tweezers, and so therefore they use the optical tweezers of Arthur Ashkin. That's what I tried to mention. Since how can I see the YouTube questions?
Sir, there is just 1 question from YouTube. May I read it out to you? It is there. It is pasted in the chat box here also in the Zoom.
कैसे देखे बोल?
When I'm pasting it again, I will paste it.
हाँ, दोबारा से पेस्ट कर दो ताकि सर को दिख जाए वो वाला क्वेश्चन थोड़ा ऊपर चला गया.
ये तो सभी बंद हो गया.
Dr. Binda, you can also read this question.
हाँ, सर मैं एक बार पढ़ देती हूँ. आप भी देख पाएंगे सर. थोड़ा सा अगर स्क्रॉल करेंगे अभी तो आ गए. मैं एक बार पढ़ देती हूँ. The question is by Mr. Manish Khare from YouTube.
Yeah. It is not so that the image transmission may also be considered as a form of communication. The image transmission, जैसा पहले initially it was thought, and it is still used to see the image. It is not communication. The communication is that you pass information in the form of digital pulses. And that is how I imply the communication. अच्छा, ठीक है. बाकी सब clear है. I think
yes,
all are clear. And our next speaker is also here. So I also look
sir, you speak so well that everything is crystal clear. Thank you so much, sir. Thank you. And I think Trista has Professor Rajaram joined. Can you?
Yes, ma'am.
Oh,
Yes.
Yeah. Good morning, Professor Rajaram. Good morning, sir. It is certainly a pleasure to have you here. I heard your talk, the talk you gave for IAPT, and it was so good. And that is why, I kind of pursued you to give this talk, because
Thank
the
you.
students will be immensely benefited. I know you're such a good speaker and you talk so well about the basics that it is absolutely, so good that you get inspired to listen to you again and again. So now before I invite you, sir, to give your talk, so I would like to give a brief introduction to the participants. So just a minute, sir. Give me 1 second. Yeah. So Professor Rajaram is going to talk about 4 phases of entropy. And I would like to read out his introduction. Professor Rajaram
Dr. Bindal, your screen is not coming.
Oh, sorry. Just a minute. Give me 1 second. Give me 1 second. I'll just share my screen again.
Yes, now it's there.
Yeah. Yes. Professor Rajaram Nityananda studied physics at the Vivekananda College and Indian Institute of Technology in Chennai, and later worked for the PhD degree at the Bangalore University in the areas of optics and crystallography at the National Aerospace Laboratory. After joining the Raman Research Institute in Bangalore in 1975, he worked mainly on theoretical aspects of astronomy, such as image processing, gravitational lensing, and gravitational dynamics. In the year 2000, he moved to Pune as the Center Director of the National Center for Radio Astrophysics of the Tata Institute of Fundamental Research. He retired in 2013 and since then has taught physics to undergraduate students, first at IISER Pune and for the last 6 years at Azim Premji University in Bangalore. He is a fellow of the 3 science academies in India and has served as editor of physics and astronomy journals of the Indian Academy of Sciences. From 2014 to 2017, he was the chief editor of Resonance, the Journal of Science Education, and has also written many articles on topics in physics and astronomy in that journal. So it is a privilege to have you here, sir, and I'm sure the students will be benefited a lot from your deep understanding of the subject. And I invite you to start sharing your screen and sir, present your talk, give your talk.
Thank you very much.
Yes, sir.
As all of you heard, I have also worked in optics, but I think giving an optics lecture after Professor Khattak would definitely be inappropriate. But fortunately, I have another interest, which is thermodynamics. And this talk is on different aspects of entropy. Okay. So I think of phases as different phases in the development of the subject, and also the phases of someone whose pictures you can see here. Right? You could say the subject started in the early 19th century, with the work on heat engines by Carnot, and which was taken to a very different level, raising a very general concept by Clausius. You can see his picture here. And then the concept was ministerial. Boltzmann and then others following him gave a statistical interpretation. And then in the 20th century, middle of the 20th century, this became the foundation of a mathematical theory of communication, what today we would call IT or ICT, which all of us depend on in our mobile phones and computers. And physicists sometimes do not hear the name of Shannon, though it has become more popular in the literature. And this is Shannon, who actually is an engineer, trained as an engineer, remained an engineer all his life. And today the concept has become even broader because in various fields, even including what you call machine learning, a concept relating to entropy was, of course, widely used, but one of the great advocates, physicist called Jain, who has also contributed to optics, something called Jain's Commons model, is a passionate advocate of this particular point of view in statistical inference. But this really goes back to, in fact, the 18th century work by Bayes and Laplace. So this is the kind of story I would like to tell you. And I'll tell you the story in the reverse chronological order. Okay? So we'll start with statistical inference. And in some sense, actually, when preparing this lecture, I realized that conceptually, this is probably the hardest. Anyone who has taught thermodynamics, including Professors Pushpa Bindal and Seema Gupta, my hosts at this meeting, will realize that it's really hard. So we will travel in the reverse direction. So I'm starting with something which happens in every physics lab. You are given some data, which is plotted on the y-axis, is a function of something else on the x-axis. X is under your control, and y is something which you measure. And you expect from the theory some kind of line relationship between them, given by this formula. But because of experimental errors, these points will not lie exactly on the straight line. Okay, so that very familiar situation is represented in this diagram. It's also represented in this equation. So I refers to the point I equals 1, 2, 3, 4, 5, 6. So at each point, you don't know the slope and intercept of the line; they are unknowns. But you expect the corresponding value of y to be related to x by this equation. And the crucial point are these errors. And I've used the symbol n because they are in fields they are called noise, right? Random errors, unpredictable errors. Okay. Sometimes they are also called residuals because your model and the measurements do not exactly fall on your model. So you have some residue, unexplained. Unexplained, but you know something about it. You know it's due to your experimental errors. And even without any formal training, any reasonable person would draw a line like A and would not draw a line like B. Okay. So why is that? Let's ask. Now, you get some insight by looking at the residuals. So in line A, this residual is positive, this is negative, this is slightly larger, these two are positive, this is larger and negative, this is again positive. It's a kind of reasonable behavior for some random measurement error or error due to some disturbance and so on. If I believe that B, suppose I have a theory which says M and C have the values corresponding to B, then I will have a problem because all the residuals are positive and they are pretty large. So we think that the solution A is more probable than the solution B. So this notion is made more formal, right? In this. So if you fix the value of M and C, then that model gives you certain residuals. Then we ask, what's the probability that these are the residuals? So I'm here using the famous Gaussian distribution. N1, N2, N3, each has a Gaussian distribution, and I have multiplied that. That's all I have done. So exponential minus N1 squared over 2 sigma squared is the Gaussian distribution for real N1. And multiplication, of course, means that you get sum in the exponent. They are assumed to be independent. We are using the multiplication law of probability for independence. Now, all other things being equal, we would like a solution which is more probable, right? So we would make all the n's very large, then this will become very small and our solution will be improbable. So we maximize this quantity. And because of this minus sign, it means we should minimize this quantity. So this is the sum of squares. And this is the Gaussian distribution, and it's Gauss himself who invented the method of least squares, which we all use very comfortably. Now, in the bigger context of statistics, this quantity is called a likelihood. Okay? Likelihood of what? Likelihood of the model described by our two parameters, M and C. So we are maximizing likelihood. And intuitively, this is a very reasonable thing to do. But you can see that even our least squares is not a sacred recipe. It comes from a particular set of assumptions that the distribution is Gaussian, that the different errors are independent. And it's always good to keep in mind this assumption, because there could be situations which you may encounter where this is not the appropriate thing to do. You may maximize some other quantity. So that's just telling you that even familiar least squares has some logic behind it. All right. Yeah. Now I am coming to the concept of information, which was developed by Claude Shannon. Okay. And I'll give you the context. Well, first, let me just information in a somewhat popular way. And I can even claim that this is my personal experience, because 30 years ago, I was an anxious father standing in the corridor of a hospital outside the maternity ward, and I saw a sight something like this. And in those days, we didn't take ultrasound to find out anything about the baby that's going to be born. So the nurse comes with a bundle like this. And at that time, there were two possibilities, right? Boy or girl. Right? So W is the symbol that we will use for the number of possibilities, especially when they are equally probable options. And they are equally probable by and large. Under natural conditions, the number of probability of a boy and probability of a girl are equal. Sometimes called one bit of information. Now, the very interesting concept, you might almost call it a philosophical concept, introduced by Shannon, is the following. Okay, that is, before this nurse told me it's a girl, this is what she told me, I was ignorant. So W was equal to 2. Okay? And of course, the ignorance was removed when she gave the answer, right? And that's the information. I got one bit of information. So a good measure of information is if you have a good measure of the ignorance received the information or the message. Now, I want to bring out one more property, because in the same hospital, of course, there are many maternity wards. There are many fathers standing outside the wards. And these are presumably independent events. So each one has W equal to 2, and I have shown 6 of them here. So the number of possible answers is 2 into 2 into 2, etc. 6 times 64 possible answers. So this is the case where W is 64. And it's 6 bits of information. So if you wanted to represent it digitally, you could use a symbol 0 for a boy and 1 for a girl. And then the outcome of this experiment, or the message received by these fathers, is really a string of 6 bits. And that's the logical way to look at it. Okay. So whereas we multiply the W's here, it makes, if you want a model, a reasonable measure of information, we should really say that we are adding the information from all these 6 locations, independent locations. And the way to convert a product into a sum, all of you know, is to take a logarithm. Okay. So this is the formula given by Shannon, right? Simplest version. So you have W, and if you had H bits of information, right? And the total number of possibilities will be 2 raised to H. That's what we just saw. So H is log of W to the base 2. Now, of course, this is very elementary, but the genius of Shannon was that he generalized this. When the alternatives are not equally probable, when the different experiments are not independent, and his basic approach was to treat the process of communication as a random process. Okay, so there are at the two ends, there is someone who's trying to send a message and someone who's trying to receive the message. Okay, and clearly, if the person already knows what the message is, then there is no need for the message to be transmitted. Therefore, to start with, there is a W or there is an H. Right? And then when the message is actually received, this is the gain in information for the receiver. Okay. All right. Now, suppose the probabilities are not equal, 1/4 and 3/4. Okay. Then how do you do this? So Shannon gave a formula to calculate it. Even in the case where the two probabilities are not equal, you have to take the average of logarithm of p. Okay. So if you do that calculation, it's quite simple. You will conclude that h is about 0.8 bits. In fact, as an extreme case, right? Suppose the probabilities were 0 and 1. That means you already know what the answer is going to be, and then your information will become 0. Okay. Now, this is interesting. What it means is, if the probabilities are unequal, okay, well, let's take an extreme case where the probabilities are 1% and 99%. Then you can do something interesting. You can take this long message, which has mostly ones and a few zeros, and you can compress the message. Instead of sending that large number of ones, you can simply indicate which are the positions where the zeros occur. And then you would have successfully compressed the message. So Shannon's theory gave you the extent to which a message can be compressed. In fact, his paper begins with the example of just the English language, right? Where even if there are spelling mistakes, you're able to correct it and you're able to understand. And nowadays, especially members of the younger generation, use a highly compressed form of English for SMSs. And at the other end, the receiver is able to interpret it and able to. So this is an example of compression. The same mobile phone is also an example of something called error correcting code. Okay. And both these are very important. So for example, when you stream a movie, right, the communication channel over which it comes has many glitches, as you very well know. In spite of that, you get a perfect file of the movie and you're able to play it. So, and the theory behind that is really based on this very fundamental idea that you can compress a message, and also if you have a channel which has a certain amount of noise, you can correct for it by a proper coding of the signal. Okay. We will come back to Jain's later. Now, so I'd like to make this example of error correction a little more vivid for you. Right? So a person is supposed to send a string of numbers, n going from 1 to 20. But let us say this is an artificial example. The device or the person transmitting it randomly, sometimes does nothing or sometimes adds or subtracts 1. Can we still find out the original message? You can. You have to create a code of this kind. You want to send 1, 2 up to 20. Okay? But you transform these numbers n to 3n minus 1. So it becomes 2, 5, 8 and up to 59. So now what happens? When your message is 2, the person may either send 2 or send 1 or send 3. But so long as we have a model for the noise, you know that nothing else can happen. Therefore, if you receive any one of these 3, you know that what was transmitted was 2. Similarly, if you receive 6 or 5 or 4, you know that what was transmitted is 5. Okay? So each of these genuine messages is now protected from being mistaken for other messages, right? And they do not get confused. Now, this is a very simple example. This is not like this. Okay. So the brilliance of Shannon's theory is that even when you have a very realistic model of noise, like Gaussian noise, sending voltages over a telephone line or optical fiber, right? You can cleverly encode in such a way that you can control. But what is the price you have had to pay? See, if there was no noise, you could have sent 60 numbers. But because of the presence of noise, you're only able to send 20 numbers. Okay? So the famous formula of Shannon is that the capacity of this channel is obtained by taking the W for the channel is capable of sending, but dividing it by the W of the messages. Okay. So the general philosophy is that if you want to do compression or if you want to do error correction, you need what is called redundancy. Right? there is multiple messages at the receiver's end will correspond to the same message at the other end. So this is the formula. Right? You have this number of messages, but for each message, the noise can further multiply it by W, and that is the number of states which have to appear at the output channel so that you can decode and get back your message. Now, this formula is not usually written this way. It's written after writing the logarithm, okay? And it's also written taking this noise to the other side, okay? So log W, that is capacity of sending messages, will be related to the signal which you receive minus, that is in logarithmic terms, minus the noise. Okay. So this is after taking the logarithm. So this is called the famous Shannon channel capacity formula. I have simplified it. And I can assure you that he did some very good mathematics, original mathematics, to prove this in many general cases. And after that, of course, people have the theme much clearer. All right. Now we have gone one step backwards, right, to Boltzmann entropy. And you must have noticed that log W, of course, that log goes to the base 2. This log is to the base E. Okay. So this is a famous formula, which you can see in any statistical physics book. Okay. Boltzmann's constant has the units of energy divided by temperature. Okay, so it could be joules per degree Kelvin. In fact, 10 to the minus 23 into 1.6. But that's really just to give entropy the familiar units, okay, of heat divided by temperature. But the real heart of entropy is in taking the logarithm of W. Now, what is W? Now, what you learn is that you have a system, like say the air in the room, you know approximately the number of particles, let's say. But we, of course, have no idea about the exact state of what each molecule is doing. Now, that kind of knowledge would be called a microstate. Okay. Now, we are ignorant about that. There are many, many microstates which are all consistent with the same total energy and the same total number of particles. And so, the methodology introduced by Boltzmann is that you have this macroscopic state, all right? You count them and you calculate the entropy. So here's an example. Right? Now, without actually doing detailed calculations, just from the intuitive idea of W, that it's related to the number of possible states which the system can have, given, of course, some constraints, right? In this case, let's say the gas temperature is known, the gas volume is known. Okay. So I've just taken this formula to illustrate the concept. So the entropy is proportional to n, the number of particles, and each particle occupies, there is the overall volume V available to the particles. Okay. And the particles also have a certain temperature, which means that the speed of the particles is restricted to some region, not rigidly restricted. There is a Maxwellian distribution, but it's concentrated in a certain range of velocity space, and it occupies a certain region in our ordinary three-dimensional space. Okay. Now, actually, velocity is proportional to the square root of temperature, and there are three components of velocity, which is we have this power of 3 by 2 here. Now, this is the formula for S, which is also a formula for W. Now, what does the second law of thermodynamics say? Okay. It's very reasonable. It says that, look, this is your ignorance. Now, the ignorance cannot decrease. Okay? You cannot get knowledge just like that, further knowledge about the system, unless you make some measurements. Okay. So, however it may ease, right? That could happen. Some processes might actually spread the system out, either in volume, and we'll see an example, or in temperature, okay, by contact with another hot body. So the message of this very brief discussion is, you can't just reduce V or reduce T without paying some price. So for example, if you just compress V by a piston, you have what is called adiabatic compression, and T increases. All of you know that, right? On the other hand, I may say I will do an isothermal compression, right? I will compress. Then what happens? Then, of course, your temperature stays the same, but whatever work you do goes out as heat. So the entropy increases outside. So you cannot really beat this. So, Boltzmann not only formulated the concept of entropy in terms of W, in terms of the statistical aspects of the system, but he also was able to justify the second law of thermodynamics. Now, if you go further back, even one step, okay, this is before the work of Boltzmann. And remember, the kinetic theory of gases was created sometime in the middle of the 18th century. Right up to almost the end of the 19th century, end of the 19th century, there were even a few skeptics who didn't believe in atoms, right? So the science of thermodynamics could not be based on atoms. It was based on the macroscopic behavior of systems. And here it's really interesting that a very important role was played by a purely engineering problem, the problem of maximizing the efficiency of a heat engine. Now, the heat engines themselves came very late in, let us say, in the previous century, right? The steam engines and so on. And they were very, very inefficient. You would consume a huge amount of energy with coal, and the amount of mechanical work done would be, a few percent of that. And gradually, just by using various tricks, engineers improved the efficiency, but they could never make it 100% efficient. And the deep reason for it, the physical reason, was given by this gentleman, Carnot. He gave a very clever argument, and I urge all of you to read it from your thermodynamics books, saying that a maximally efficient engine will also be a reversible engine. So to explain this in very simple terms, which is appropriate for a brief lecture, I could say that the job of a heat engine, let us say you're driving a pump in your household, right? So you have to give it some energy, right? And then it does some work. Okay, sorry, let's get back. It does some useful mechanical work for you. Okay. So, for example, it might be a diesel pump. So you would have the diesel burning, and that will be a hot part. Then it'll have an exhaust, which will be the cold part. So it's transferring heat from a higher temperature to a lower temperature, and some of that energy is being used up to pump your water. Now, in the same house, you may have a refrigerator, which now takes in maybe energy from the electrical supply, all right, or even from a diesel generator, it may take, all right, and then it does opposite lower temperature to higher temperature. Now, the beautiful argument of Carnot is that let us say one of these is reversible. Let's say the refrigerator is reversible. It can also be run as an engine, whereas the other one may or may not be reversible. Then he realized that by coupling these two, you should never be able to transfer heat from a lower temperature to a higher temperature, because that would be contrary to human experience. Okay, just like that. And that's how he used. Now, that was specifically in the context of heat engines. But this was taken even further by Clausius. Okay. But interestingly, all this was quite independent of understanding what is happening inside the substance. Could be a gas, could be a liquid. So, and therefore, it was a very general concept. Okay. Again, the concept of reversibility was very important. All right. So you could always have a system giving out a lot of heat and increasing entropy. But if you do it in the most efficient, reversible way, there's a minimum value for this quantity. Right? And that he singled out. I think it's actually a great achievement, because the physical meaning of this was only understood decades. So just by this kind of reasoning, he introduced the concept of entropy. And while it was mysterious, people didn't wait. They started applying it in chemistry. I mentioned the name of Gibbs. It applied, of course, in engineering. And we have already seen the later applications in mathematics as well. So I'm illustrating this. absolutely the simplest example of entropy increase. Okay, namely, this is a container or a room even. It's got a partition. It's got an opening. The gas molecules are on one side. Okay, and then of course, let's say the opening is closed. Then the opening is opened, and then the gas molecules. Common experience tells you that the gas molecules fill the whole container, and then you can wait forever, but you will not find all the gas molecules going back on one side. You will be able to go from this state, macro state, to this macro state, right? But this is forbidden. I have put X here to tell you that this is forbidden. This is a one-way street. Okay. One thing you can immediately see is that this depends on the number of molecules being very large. Okay? Suppose there had been only one molecule here. Then, it would have come through and it would have come back, it would have come through. So you would have been happily going back and forth between these two states. So the argument that you go from here to here and you don't go from here to here has to be a statistical argument. Okay, it doesn't apply when you do it with very small molecules, small numbers of molecules. And this is an aspect which we don't normally associate with the name of Einstein. We think of photons, we think of relativity, but actually Einstein's first love was thermodynamics. And he realized that, and at a very young age, even before his relativity work, in fact, that was his PhD thesis, that if you're dealing with a very small particle, right, they will see fluctuations, which apparently go in the opposite direction. So on a big scale, friction will always bring an object to rest. But on a very small scale, a small particle in a fluid, friction will bring it to rest, but the bombardment from the surroundings will again give it some speed, will again come to rest. Its velocity will fluctuate. Okay, so that is the sense in which we should understand the second law of thermodynamics. There is another interesting aspect of this. Now let me see if I have it. Yes. Now Maxwell was a contemporary, again more famous for his electrodynamics, but he worked on the kinetic theory of gases. His distribution of velocities is well known. But he also came up with this very interesting idea. So going back to the previous picture. Okay. Yeah. He said, all right, this is the situation in which you have the entropy has increased. Now I'm going to put, he didn't call it demon, but later on people call it demon, some being with tremendous powers, which is a gatekeeper here. Now the gate is closed, the molecules come from this side, the gate is never opened. So it hits and bounces back. But if a molecule comes from this side, the demon opens the gate and the molecule gets it, closes the gate again, and keeps on doing this selectively so that you could actually go from this state to this state. Right? Now, this is a different kind of apparent violation of the second law of thermodynamics. Right? The other kind, which simply depends on small numbers, we understand. It's because the second law is a statistical law. And as I said, that theme was very well developed by Einstein in his theory of the motion of small particles in a liquid, which we call Brownian motion. But this Maxwell's demon raises some interesting questions, right? Is it possible to actually send things in the opposite direction from larger entropy to smaller entropy simply by some kind of very careful, intelligent observations? Now, this question worried scientists for a while. Maxwell himself does not seem to have given an answer to this. Okay, and various people took it up in the 20th century, and there are a couple of names that I would like to mention in this context. Okay, one is a scientist called Szilard, not very well known, and if at all people have heard his name, it will be in the context of the development of the so-called hydrogen bomb. Okay, but before he worked on that, he actually said, let us take this demon seriously, but the demon cannot have supernatural powers. It has to also obey the physics. Okay, so he thought of various thought experiments. So the demon may shine some light from here to, and look at the molecule, and, measure its velocity, right? So he made it a physics problem rather than a philosophical problem. And then by careful analysis, he was able to show that yes, you might decrease the entropy of this gas from going from here to here. But in that process, all these measurements, like sending a beam of light, and then if the beam of light gets scattered from the molecule, you have to detect it. So analyzing carefully what happens in the detector, you find that in every case, provided you do not have information to start with. If you have this information to start with of where these molecules are, where they are moving, then of course you can reduce the entropy, right? Because you have that information, which is like a negative form of entropy, which is we have already discussed. But if you don't have that information, you will shine the torch and sometimes it won't hit the molecule, right? Then similarly, let's go to the detector. Okay. Now detector has to be kept at a very low temperature, because otherwise sometimes the detector will show you light which is not coming from the scattered light being scattered by the molecule, but it's just coming from the surroundings. So then the surroundings have to be very low. So then you ask what happens to the detector. In every case, Szilard and all his people who followed up realized that if you think of this Maxwell's demon as obeying known physical laws, then you are not able to really decrease the entropy. Okay. So second law of thermodynamics is preserved. Now matters remained at that point till we came to the age of computation, 1960s, right? And again, we have this very interesting connection between engineering and physics. So IBM, of course, as you know, is a company which makes many do now, but they were the pioneers. And at IBM, there are two people, Bennett and Landauer, who gave us another interesting way of thinking about this object. They said, okay, the initial state is supposed to be random because it's a state of higher entropy, right? Then you have this daemon. So the daemon actually notes down which are the, for all the molecules, right? It has to look at the molecules on this side as well to prevent them from coming. And it has to look at the molecules on this side to allow them to come. So let us say the daemon has successfully done its job. Now what happens after that? Okay. So what happens after that is that the gas has decreased, but now this daemon, and of course being a modern daemon, it has a computer, has a large string of ones and zeros representing the information about which molecule was going in which direction. Okay. And they argued that this string of ones and zeros in the computer also has an entropy associated with it because it's a random string, right? It's not something you can predict because the initial state of this system, this gas, was also random. Okay. So then they said, fine. So maybe entropy is not really decreased. Okay. Because we have these random strings of ones and zeros. But then you can say, I can delete them, right? I can delete the ones and zeros from my computer. So computer has come back to its original state. And now we have truly decreased the entropy. But they made a very deeper analysis of this. And they then started to make a distinction between reversible computers and our normal computers. Okay. I'm making this. So a reversible computer is something where you have an initial state and some physical processes happen in the computer and you have a final state. And that is what you're interested in. So it has done the computation for you. Okay. But you have not expended any energy in that process, let's say. However, this computer remembers everything that it has done. Okay. So when it does the next computation, because it's reversible, all the computations that it has done in its entire lifetime are accessible to you. Okay. Now our computers are not like that. If they were like that, if they had stored all the information which was given to those computers, all the programs from the time it was manufactured, then they would be useless. Right? So they realized that a very crucial part of computation is erasing the old information. So they looked into the process of erasing a bit of information in a computer. It's a physical process. You have a tiny piece of ferrite or some magnetic thing on a disk, and it has two possible states. And then it comes to one possible state from standard erased state. So again, this is a physical process, right? And in this process, because initially it's random, it could be 1 or 0, and then it goes to the same final state. So W has decreased from 2 to 1. And if you analyze physically how you erase, again, you find you're generating some heat somewhere. So it looks like the second law of thermodynamics and the concept of entropy, we may try to avoid it as much as we can, but ultimately it catches up with you. So both in the explanation of Maxwell's demon, in the modern concept that there is a cost even of erasing a bit from a computer, okay, we find this aspect of entropy coming out. So this is the summary of what I just told you. The first part is that the entropy is transferred to the daemon, and then it's because all the useful computers that we have are actually reversible, okay? Because they erase information, and ultimately they give out heat to the surroundings. I'd like to conclude with a difficult question, a question which, at least to my mind, is not that very easy to answer. And this is a question which worried Boltzmann and has worried many people ever since. If you take the second law of thermodynamics and the concept of entropy very, very literally, then our world should be getting more and more disordered. Okay. So what does that mean? If you have any difference of density or difference of concentration or difference of temperature, these differences will all get equalized. And people worried about it. They even coined a term called heat death. The universe will grind to a halt. And once you reach an equilibrium state, nothing interesting happens, right? And the philosophically minded physicists also worried about this, because you look around you, you don't see heat death, okay? You see a system with tremendous structure and order. So this is from a national park in Kenya. So this is the famous mountain there, Kilimanjaro. It's an amazing mountain because it's exactly at the equator, but it's covered with snow, which itself tells you, right, that you have cold objects coexisting with hot objects, and you have clouds, you have life, which is an amazingly ordered phenomenon, right? And you have trees, you have grass. I mean, this is the world we live in. So when I say who ordered this, what I have in mind is, how did this order really emerge? And a partial answer is given by cosmology. All right. Now, we always assume that the increase of entropy makes systems more uniform, but there is an exception to this. If you have a system where the force of gravitation is important, okay, then it can happen. And in fact, there is a famous result in the dynamics of gravitating systems, which justifies what I'm saying, that above a certain size, the system increases entropy by becoming non-uniform. So if you take an example of a star, for example, it's hot on the inside and it's cold on the outside. Right? Higher temperature in the center and cooler temperature at the surface. And then, of course, the radiation is going into space, which is at a still lower temperature. Okay? And it's irreversible. All the radiation is flowing out. But what is the final effect on the star? Interestingly, the star is losing energy. But remember, gravitational energy is the negative quantity, right? It's a binding energy. So when it loses energy, it gets more tightly bound. So the star may shrink, right? And then the center will become even hotter. And this is actually the way stars evolve. Like our sun, billions of years from now, its center will become even hotter. Okay, it'll, instead of consuming hydrogen, it'll start consuming helium. Similarly, on a bigger scale, if you look at our current model of the universe, which is very well confirmed by observation, if you go some 13 billion years back, the universe was very uniform. There were no stars, no galaxies, no planets, nothing. Just a more or less uniform temperature, more or less uniform density. The more or less is important, not perfect. So then if you have a small increase in density, gravity ensures that surrounding matter will come and fall on that. And that is how you form galaxies, stars, planets. So the universe becomes more uniform, even though its entropy is increased. That's part of the answer. Up to the planet. Now what happens on the planet? What happened on Earth? If you analyze, have our lunch shortly, right? I'm sure you're all waiting for it. Where did that lunch come from? Maybe from trees, maybe from animals. But where did they get it from? Ultimately, you will trace it back to the sun. Okay. Now, of course, we receive energy from the sun, but the Earth is not getting hotter and hotter. Right? Well, it is because of climate change. But otherwise, before we started polluting the atmosphere, we had a more or less constant temperature. That's because the Earth ultimately radiates the same amount of heat into space in all directions. Also, what comes from the sun is in the visible region. What is radiated is in the infrared region. So again, if you do the balance of entropy, you will find that the entropy definitely increases. Excuse me? Okay.
No, sir, please continue.
Sure.
Please continue.
Yeah. Right. So in a way, our Earth is like a heat engine. It's taking in energy at a high temperature and putting it out at a lower temperature. Okay. And converting some of that to useful work. Okay. So the plants convert sunlight into many of the things that we eat. And of course, the proteins that we eat, many of them, of course, even the proteins, the animal proteins that we eat, ultimately those animals feed on other animals, which sometimes feed on grass. So it goes back to the sun, photosynthesis, the bacteria in the roots of plants produce, the dal and protein. So in all these cases, we can see that we have a source, which, if you like, has a certain entropy. And then the net result is to increase the entropy. But in this process, we have actually created order. Okay. Now, that is the current situation. Okay. Someone can sort of rationalize it, sort of explain it by saying, yes, the second law of thermodynamics is not violated. We are functioning like heat engines. And since we are not 100% efficient, we are not reversible. So if anything, we put out more entropy than we take in. Okay. Those of you who have seen that famous heat engine equation will appreciate. I could simply say Q2 by T2 is greater than Q1 by T1. Okay. But actually, the mystery is deeper than that. After all, there was a time when we were not here. You had just a very hot planet, maybe with gradually oceans coming. How does life emerge? So, on the one hand, we believe in the concept of entropy. It's very well established. But we should not think that the laws of thermodynamics, the law of increasing entropy, prohibits the emergence of a lot of order, a lot of structure. Right? In fact, it appears, and a lot of 20th century physics has actually gone into trying to answer this question in very simple systems. Okay, how do you get structure? So, for example, systems which people call given for a kitchen, right? You have an object placed on the gas flame, liquid, right? And it's being heated from below. Now, it could have just uniformly heated up, right? But that's not what happens. What happens is you get some kind of convection happening, right? So the liquid rises, hot liquid rises, the cool liquid falls, and some kind of order develops. So this is entire development in 20th century and 21st century physics that, consistent with the laws of thermodynamics, we are still interested in various irreversible processes, which on the one hand, they increase entropy, but as a side effect, the interesting structure. So this is really a very open theme, which is being explored by biologists, explored by physicists, and explored by astronomers. So the formation of structure and the formation of order involves what we could call the flow of entropy. Okay, so entropy is, so entropy is more than that, is generated in the system. So this this kind of is a major current theme. Okay, and many people, including many people in India, work on this theme. In fact, since you are all in Delhi, one of the people in Delhi University, a good friend of mine, Professor Sanjay Jain, I think many of you may have heard of him. When I got to know him, he had just finished his PhD and he was working in string theory. And then he joined the Indian Institute of Science. And after some time, he decided that this was a more interesting problem. So in fact, he has done some very interesting work on how you can have the emergence of order. So I'm just throwing out this hint, since he's available to you in Delhi. Hopefully the lockdown will end. You will all meet people face to face. Of course, I have to thank the lockdown because, you know, if I had been asked to travel to Delhi at my age, I might have thanks to Professor Seema, Professor Pushpabinder. Maybe thanks to the coronavirus for making Zoom lectures possible. So I'd be happy to take questions on this theme. It's a very broad theme, but I hope you found it interesting.
Thank you so much, sir. It was really wonderful and informative talk. Thermal physics is also my field of interest. You explained different aspects of entropy so nicely. Shannon Jain's theory, H is equal to log W, mathematical theory of communication, Shannon channel capacity formula, principle of increase in entropy in form of ignorance, and Maxwell's diamond, and so many things. I could not move my eyes off the screen for even a second, sir. It was a complete...
Dr. Seema, to add, this is the semester where statistical mechanics is taught in the last semester to the BSc third year students. So our third year students are learning statistical mechanics in this course, and right now they are going through this chapter of entropy and Boltzmann relation and so on. So it is the lecture has come out to be highly coincident and beneficial to the students, and in a completely different perspective. So thank you so much, sir. It was very nice.
I would add it was actually a complete understanding of the concept beyond the books, I think.
Actually that is a sign of a great physicist, that he can bring out the physics hidden in the formula so well, so easily. I mean, what you can't see directly, he just points it out to the audience like anything. That is the beauty of it.
And the relevance of entropy in our daily life, sir. It was beautifully brought out.
It was beautiful. I would thank Dr. Pushpabinder that she was praising sir a lot, and now I got a chance to listen to him. It was really wonderful, sir. It was really wonderful.
But could I add a note for the students? I mean, in a popular lecture like this, one oversimplifies. So this is not a substitute for detailed study of the textbook, solution of problems and examples, which is what will make you a more complete physicist. And I can also assure you that I went through the same process, and not only in my BSc, MSc, PhD, but also in my research. But of course, now and then it's good to come back and look at the concept in a broader way and bring out the connection with the real world. So I hope that on the one hand, you liked whatever I did, but on the other hand, you will continue to become professional, serious physicists.
So it was really a wonderful talk, sir. Even in chat box, we don't have any question. I think it was so crystal clear. Everything was so beautifully explained that we don't have any question in the chat box. Because I'm not able to see any question. So
I'm seeing one.
You're able to see one, actually.
Image transmission may also be considered a form of communication. Is that the one?
Sir, that is
audio signals.
That is for fiber optics.
Okay. Okay. Interestingly, I did talk about communication. Okay. But answer is yes, I'm sure.
Yes.
You can transmit anything which can be represented in bits. Okay.
Yes, we can see such good comments about your talk, and once again, we all thank you from the core of our heart. Yeah.
Yes, sir.
Okay.
Thank you so much.
Sorry for tuning in a little bit late. There's something.
No issue.
No, sir. You were well in
No
time,
issue.
sir.
You're well in time.
You were well in time. Thank you so much.
Thank you
sir.
so much, sir. Thank you so much.
So with this,
The
we are
feedback
completing.
link is shared
I
with
will.
the participants.
Okay.
Yeah, the feedback link is shared through the registered email ID. So you kindly fill that form because it is open only for a few minutes. So it has been mailed to you. So and please, yeah, Dr. Seema, please announce.
Yeah. So with this, we are completed with the first half
Morning
of presentations from eminent speakers. So as Dr. Bindal told you that we have provided feedback forms on your mail. So please fill it. It will be open only for 10 minutes and it is also required for your certificate. So please fill it. So now we take a break for lunch. We request all of you to join back sharp at 2 p.m. for the next set of presentations from Professor Anurag Sharma and Professor Vijay Singh.
Yeah, please look forward to those talks because they are again going to talk about very basic concepts and you are going to study these in your curriculum. So do come back on time and you can definitely look forward to these talks.
Yeah. So let's meet at 2 p.m. sharp.
Yeah. Okay.
Bye then. Enjoy your lunch.